Welcome to our video on Bayes formula. We're going to go through 5 examples today of some typical probability questions that require, well, not require, but benefit greatly from using Bayes formula. Most of these, if not all, can be done without Bayes formula, but it really does make it a lot easier. So even though I'm not a proponent of being a slave to formulas and always using formulas, this is one instance where it's a good idea. It is very helpful. So if you can put it in your notes and use it, it'll save you a lot of time. So here's a typical example where we're just given a bunch of probabilities listed out, with symbols of what's going on and really no help whatsoever, no context, no pictures, no nothing. It might be helpful then to draw a picture of your probability tree or your decision tree. Now, with all of these questions, the first thing you always need to identify is the question, right? What are you looking for? You're looking for the probability of m given n. And we know that according to Bayes' formula, that the probability of m given n is going to be the probability of m times the probability of n given m, and then we're going to divide by a sum, that's a sigma for sum, of a bunch of these same things. We're going to have this exact piece and then all the other pieces that are involved in this particular situation. Now this one only has two groups. It's m and not m, right? They tell you that it's just m and then there's this n thing, and then we'll have the complement, and that's about it. Okay, so let's start filling in our tree, right? We know that we need the probability of m, so they tell us that we have m, and then of course our only other choice is m complement, right? The thing that isn't m. And this is 0.7, so this one of course is 0.3. And then from each of these branches, we're going to have n and n complement, right? And complement. And they tell us here the probability of n happening given that m has already happened. And that's this first branch, right? Because m has happened and now we're going to do n. That's 0.2. So we now know what this one has to be, right? 0.8. Then they also tell us the probability of n happening given that m prime, right? M complement happened is 0.7. So that's this one down here, 0.7, and then of course 0.3. So we could very simply do the probability of all these branches, right? To get to this spot here would be 0.7 times 0.2, 0.14. This one, 0.56. This one here is 3 times 7, so that's 0.21. And then this one here, 3 times 3, 0.09. And you'll see that if you add them all up, they add to 1, right? This is 60, 70, right? 80, 91, and then the 9 gives us to 100. And that's the way it should be. So now, the probability of m given n, well, given n means that we're only concerned with those branches that come from n, right? So in theory, that's our new given. And remember, I've talked about this in other videos, that the given condition just reduces our population. So instead of having these 4 possible outcomes, we only have these 2, because those are the only ones that are given n, right? That n actually happened. N is in Nancy. And out of those 2, what's the probability that m happened? Well, that's only this top one, right? Because that's when m happened. So we know it should be 0.14 over these two numbers, 0.14 plus 0.21. So we get 0.14 over 0.35. And then if you have one of these My Math Lab questions where they tell you you have to list it as a decimal or a fraction, then the trick to turning this, as an integer or a fraction, the trick to turning this into a fraction is just multiplying by powers of 10 to get rid of the decimals. In this case, because you have 2 decimal places, you have to multiply by 100. And this becomes 14 over 35, which of course are both divisible by 7. So 2/5. And that would be the answer for this one. And you'll notice we didn't use Bayes' formula. But if we did want to do it with Bayes' formula, it's very simply just going to be, right, probability of m given n is equal to the probability of m times the probability of n given m, and then all over this thing again, and then plus all the other cases. And since we only have 2 groups, m and m prime, then it's probability of m prime times the probability of n given m prime. Right, that's the formula. That's how it works. And you can see that this lines up to exactly what we did. This top number, probability of m, is 0.7. Right, that's the 0.7. This probability of n given m, well, here's n happening given that m has already happened. That's 0.14. And then those, of course, are down here as well. Sorry, I'm an idiot. It's not 0.14. I'm looking at the answer instead of the actual number, right? It's 0.2, duh. So 0.2, 0.2. Okay, and then probability of m prime, that's just 0.3. And then n happening given m prime, n happening right here is 0.7. And when we do the math, right, this is where we get 0.14, this is where we get 0.21. Of course, up on top, we get 0.14, and you can see we have the exact same thing, 0.14 over 0.14 plus 0.21. So it's kind of a visual representation of how and why Bayes' formula works. All right, let's look at another one. Here's the same example, only now we have 3 categories, right? Instead of m and the complement of m, we now have these events R1, R2, and R3. We could still do this with a tree diagram very easily. So here's R1, R2, R3. And then you can see off of all of these, we have this Q. So either Q happens or Q doesn't happen, right? Because that's really the only thing that's happening here. Q and Q prime. Q, Q prime, Q, and Q prime. And then we could fill all these things in, right? The probability of R, 1, 0.05, R2, 0.6, R3, 0.35. You can see these 3 things add to 1 like they should. This says the probability that Q happens given that R1 happened. Well, that means if R1 happened, then what's the probability that Q also happens? That's 0.5. So this one has to be 0.5. Then they tell us Q given R2 is 0.4. So here's 0.4 and 0.6. And then Q given R3 is 0.6. So that's down here, right? 0.6 and of course 0.4. Now, what's the probability that R2 happened given that Q happened? Well, we can think of it the same thing, right? It's a given condition. So we're looking for all the branches where Q happened. So that is now our new total, those 3 branches. And we would have to calculate those 3 probabilities, and those are going to be our totals. And then out of those 3, where are the good ones, right? Well, the good one is the R2 piece, which is this one. So this branch ends up being the good one, and then the 3 of them end up being the total. And this correlates once again right to the formula, right? So probability of R2 given Q is equal to the probability of R2 times the probability of Q, right, given R2. And then on the bottom, we have to sum up all the pieces. So we're going to have R1 times Q given R1, right, plus the R2 Q given R2, and then plus the R3, and then the Q given R3. I just didn't put in the P's, right? The probability of R1 times the probability of Q given R1, so on and so forth and so forth. That's the formula. That's Bayes' formula. But if we just look at these, 5 times, right? 5, so 0.025. This one, 6 times 4 is 0.24, and then 6 times 0.35. So times 2 is 7, times 3 is 21, so 0.21. Now, if we did these other 3, we would see that all of them would add up to 1, which is what they have to do, but we don't need to waste the time doing that because we now have all the numbers that we need for this formula, right? The top number is the green one, and the bottom number is just those 3 added together. So 0.24 over 0.025 plus 0.24 plus 0.21. And again, because they want it to be a fraction, we're going to have to add all this together on the bottom and get, what is that, 45, 47, so 0.475, right, 475. So now we have to multiply by 1,000, right, 3 times to get rid of the decimals, and you get 240 over 475. And then, of course, you have to reduce that. They're both divisible by 5, and then you go from there until you get your final answer. Okay, so 2 examples, whether we have 2 groups or 3, you can see that they're both done the exact same way. Tree diagram, I think, is better than the formula, but the formula might be a little faster for you, right? Because they gave us all these things, right? We know Q given R3 is right up here at 0.6, and we know Q given R2 is right here at 0.4. So we could actually just plug numbers into this formula without drawing a tree. I like the tree. It helps me understand what's going on, but if you want to save some time, by all means, skip the. Okay, let's look at an example now where we don't have all of those funky symbols, right? They don't give us all the given conditions, and we just have descriptions, kind of like a word problem. Well, now in this case, it might be easier to put your information in a table or draw a tree, right? These visual tools are very helpful. So let's see what's going on with this one. We have Bureau of Labor Statistics. In a certain month, 32.6% of the labor force had a high school diploma or fewer years of education. So that's group 1. Group 2 had some college or an associate's degree. And then group 3 had a bachelor's degree or more. And you can see that if you add those 3 numbers up, it'll add up to 100. So those are our 3 categories. Now, of those with a high school diploma or fewer, i.e. the first group, 6.4% were unemployed. Of the next group, 3.7. Of the last group, 3.1. Find the probability that a randomly chosen labor force participant has some college or an associate's degree, given that he or she is unemployed. So as I said before, you always need to identify the question first so you can figure out how to set up the formula and all that. So this is, right, find the probability that a randomly chosen labor force participant has some college or an associate's degree. That's category 2, right? Some college or an associate's degree. So I'm just going to call it category 2. So what's the probability that somebody is in category 2 given that they were unemployed? That's a U for unemployed. And we know that according to the formula, that's going to be, I'll put it here, probability that they're in category 2 times the probability that they're unemployed, given that they're in category 2, all over the sum of all these, right? Probability that they're in category 1, times probability that they're unemployed given category 1 plus this one again, probability of C2 unemployed given C2, and then finally probability that they're in C3 times the probability that they're unemployed given they're in C3. Now, you might want to put this stuff in a table, like I said, just to kind of keep track of it. Or if you just throw it on the formula, it's pretty easy now to put everything into it. Because the probability that they're in C2 is just literally, okay, well, this was C1, right? This was C2, this was C3. So it might help to do that just to kind of keep track of the numbers, right? C1, C2, C3 was 32.6, right? 26.9 and 40.5. Yes, if we did a tree, these would have been our initial 3 branches. And then off each of those branches, unemployed or not employed, right? Sorry, unemployed or employed. So you would think of it as U and then U complement for each of these branches. U and U complement, U and U complement, C1, C2, C3. And you can fill everything in, right? 32.6. Now these are percentages, so technically you should really be writing them as decimals, 0.326, so that they'll all add up to 1 like they should, right? And 0.269, et cetera, et cetera. I'm not going to waste time drawing the picture. If you want to draw the picture, by all means do it, but I want to try and keep this video from becoming an hour long. And at this point, all we'd have to do is plug everything in. Right, so probability of C2, 0.269. You'll notice that I'm using it as a decimal and not as a percent. And then the probability they're unemployed given their C2, well, that's what all these things are, right? So they told us, I'll put a little column here, that of those with a high school diploma or fewer, so that was category 1, 6.4% were unemployed, right? These are my unemployed people. Of category 2, it was 3.7, and then of category 3, it was 3.1. Makes sense that those go down, right? The more education you have, hopefully the better chance you have of getting work, so lower unemployment rates. So this was category 2, so we need 0.037. Remember, we have to write this as decimal. And then the bottom is just going to be all of these pairs added up, right? 0.326 times 0.064 plus ... You get the idea, right? I'm not going to waste time and move on to the next one in the effort to save some time. Okay, here's another example that's pretty much just like the other one. Instead of having 3 categories and then either unemployed or not, we now have 2 categories and then with 3 things. Either the stock went up, the stock went down, or the stock stayed unchanged. But it's still the exact same idea. First thing we have to do, identify the question. Find the probability an unchanged stock was listed on exchange 1. All right, so where's the given there, right? So find the probability that an unchanged stock was listed on exchange 1. It sounds to me that they're finding the probability of an unchanged stock given that we're on exchange 1. Okay? So here would be your 2 branches, E1, E2. And then we would have the 3 different bits and pieces. So now hopefully some of you are already starting to question what's going on. Okay, because if we were going to use this as our question, then Bayes' formula, right, means that the numerator, the top, is going to be I'll put it over here. No, I'll put it down. Well, I'll put it right here. It's going to be the probability that it's an unchanged stock times, and because it's the first thing, this is F given E in the formula, is always probability of F times the probability of E given F. So probability of exchange one given an unchanged stock. And then you look at these numbers here and you go, that's not what they gave us, right? This is very clearly that the exchange stocks are the two categories, the starting categories, right? And then these are the three pieces they're broken into. So we're going to have three branches coming off of each of these. And these three branches are going to be, right, it advanced, it was unchanged. Sorry, we'll do it in order that they had it. So advanced, declined, and unchanged. And so this probability here is the probability that it was unchanged given that it's on exchange one. And that's not what we're going to need in our formula. We're going to need the probability that it was E1, right? That it was an exchange one given that it was unchanged. So everything is backwards. It doesn't fit. And that's because this is a poorly worded question that you're going to see sometimes, that it really doesn't equal this. It feels like it equals that, but what they're really asking for is the probability that you're on exchange one given that it was an unchanged stock. And so now if you use that one, instead of this mistake here, you know that the numerator is going to be just the probability of E1 times the probability that it's unchanged given you're on E1, and you go, aha, those are all the probabilities I can figure out. Those work. Okay, so sometimes the questions aren't worded intuitively, and you might start going down the wrong path, and that's why I recommend you always just draw a quick tree and then go, wait a minute, as you started filling in your formula with Bayes' formula, started putting in, the E's and the U's for exchange one and unchanged stocks, you'd see very quickly that it doesn't fit. It doesn't make sense with the context of this question, with the way they gave us the numbers. So instead, we would have to go to these instead. Okay. Now, by all means, if you want to move on to the next example, you can fast forward. I'm going to try and go through the work here quickly because this video is getting too long. Okay, so here it is really quickly. I put in all the numbers. We know that because we're looking for the probability of E1 given unchanged, we're just looking at the two unchained branches. That becomes our new total if you add those two numbers together. And then this is the good one because it became, it came from exchange one. These numbers, of course, just like before, you multiply this number times this to get that, and that number times that. Now, some of you might be noticing something odd happening here. These three numbers do not add up to 1, and neither do these. Okay? This was just some sort of glitch in the homework software. When it created these probabilities, they forgot to write into it that they need to add up to 1. Either that, or there's supposed to be some other category for stocks that we don't know about, but either the stock goes up, the stock goes down, or the stock doesn't change at all. So I can't see how there's a fourth category. So it seems more likely that it's a glitch, it's a mistake. They should add up to 1. And then of course, if we did all the rest of these, right, and had all 6 of these, those should add up to 1, and they won't. So it's a problem. It's a bad question in that regards, but we can still run the numbers and get the answers, even though it's based on bad theory. Okay, our last and final example, I just wanted to show you guys that when you start getting things like this where there are a lot of categories, and you would then have a lot of branches, you might want to just draw just the beginning branches, and then from there kind of just go with the formula or go with the number. Again, with these, the questions aren't always very clear as to what we're looking for. Probability that a randomly selected woman who's never been married is in that age bracket. That's actually asking for the probability that they're 35 to 44 given, never been married. So your first branches are going to be your categories. 1, 2, 3, 4, 5 of them. Category 1, 2, 3, 4, 5 branches. They don't have to be straight lines. So those are going to be each of your categories, right? Each of your ages. And then off of each of those, it's going to be, right, never been married or its complement. So you can just think of it as, N for never married and then N complement. And then these are all going to be the same thing. The formula is going to make it simpler, than trying to draw this picture and do everything, but the picture will help us figure out where the numbers go. Of course, all of these numbers go on each of our branches, right? 0.133 and so on and so forth. These numbers do in fact add to 1 like they should. These, of course, won't because they shouldn't, but each of these pairs would, right? If this is 0.865, we know the other one is just 1 minus that. And if the next branch is 0.354, then we know that the n prime is 1 minus that, and so on and so forth. Now, what I wanted to show you with this one is when you get all of these categories, you know that when you put this into the formula, you're going to have on top the probability of the 35, right, to 44 range times the probability of never given 35 to 44. And never given, remember these are women now, so this should have been 2, 3, because instead of these, we're dealing with these numbers here, because we're dealing with women. The never given that they're in this age bracket, so that would be this number, 0.781, and this number here is 0.123. And then on the bottom, they're all going to be paired up, right? We're going to have probability of the first age bracket. Oh gosh, sorry, I did that wrong because this is 0.219. I'm an idiot. I did the first one. And then, right, because this is supposed to be this age group, and then 0.148. Okay. And on the bottom, we're going to have all these pairs. Probability of, we'll just call it F1 for the first group, and then probability of never married given F1, and then F2, and then N given F2, ... And each of these pairs, you can see F1 is this probability, 0.123. And then never been married given first one is the 0.781. And the second one, F2, 0.194 times this one, 0.255. Can you see that we're going to multiply all of these pairs together, get a bunch of numbers out here, and that's going to be the sum on the bottom. Well, that's a lot of math to do by hand or in a calculator, a lot of places where you can make a mistake. So it might be better if you put it into an Excel spreadsheet or any kind of, there's a lot of online free spreadsheets. Obviously, you don't need to put in all of the details here. I just did this so you can see where the numbers are. So here are the proportions. Here are the probabilities of not being married, right? I'll move it down so you can see they match up, right? 1, 2, 3, 194, and so on and so forth. And then all I did simply in these cells is I just said this cell is going to equal this one times this one. And then I grabbed the corner here and I drug it down, and it copies the formula so that each of these cells is just the product of the two that are to the left of it. So all of these numbers are just the product of the next two. And then this is the one I'm looking for, right? That's the good group. That's the good. So here I just did, it's going to equal the good divided by this number down here, which was the total. And I got the total very simply by just doing auto sum. And auto sum just sums up all the numbers above it. So that would be the probability that we're looking for. And it's a lot faster than doing all that stuff by hand. That's the last tip I want to show you guys on how to use the formula. Use the trees. The trees are very helpful to see what's going on.